Hello everyone and welcome to this week's lecture. So this week we start with convolutional networks. So as we mentioned last week, we can't really deal with images as just a simple vector of input pixel values, essentially because this loses important information when it comes to the adjacency of pixels and how the intensity changes from one pixel to the next and so on. If we're able to construct a network with fully connected layers and an image as input, we would get the same result whether we trained with unperturbed images or with images all of those pixels had been randomly permuted, just because we would express each image in that case as just a simple linear vector. The network would have no idea that which pixel is near what pixel, so mixing up the pixels would make no difference. In addition, suppose there are n pixels and n units in the first hidden layer, so that the pixels are provided as input to this first hidden layer. If the input and the first hidden layers are fully connected, this means we would end up with n square weights to be trained, right? So for a typical megapixel RGB image, that would be 9 trillion weights, because the megapixel would be 3 RGB, so 3 times 10 to the 6, and then you square that, you get trillion. You get 9 trillion. So that would be a huge parameter space, that is not realistic. There's no way we will train a network with 9 trillion parameters. So all of this suggests that we should construct the first layer, the first hidden layer, so that each hidden unit receives input from only a small local region of the image. So this kills two birds with one stone, essentially. First, it respects adjacency, at least locally, right? Because you're providing a small area of the image to each unit. And second, it cuts down on the number of weights. If each local region has a number of pixels, L, that's much fewer than N, then in that case, L times N will be much less than N squared. Now, there's another property of images that we have to consider. Essentially, anything that is detectable in one small local region of the image would look the same if it appeared in another small local region of the image. So, in other words, we expect image data to somehow approximate spatial invariance, at least at a small to moderate scale. Okay, so if I see a small dog in the top left corner of the image, and I should also be able to identify that if that same small dog appears in the lower right-hand corner of the image, even though we're only training on small regions of the image at a time. We're not feeding ever the entire image. So local spatial invariance can be achieved by constraining the L weights connecting a local region to a unit in the hidden layer to be the same for each hidden unit. Okay, so this makes the hidden units into feature detectors that detect the same feature wherever it appears in the image, and that's what we're looking for. So that's what we mean by spatial invariance, is that our network should be able to detect the features wherever they happen to be in the image. So typically we want the first hidden layer to detect many kinds of features, not just one. So for each local image region, we might have D hidden units with D different sets of weights. So this means that we would have D times L weights in all, a number that is way smaller than the n square that we were talking about earlier. Not only that, but D times L is independent of n, which is the image size. So regardless how large your image is in terms of pixel numbers, it doesn't matter. That's not going to impact the duration of training for the network. So by injecting some prior knowledge, we can then develop models that have far fewer parameters and can learn much more quickly. So that's the idea behind convolution neural network. It is a network that contains spatially local connection. Okay. So a pattern of weights that is replicated across multiple local regions is called a kernel. And the process of applying the kernel to the pixels of the image is called convolution. So these are terms that you will only see with convolution neural networks that were designed specifically for image recognition and computer vision. So kernels and convolutions can be, looked at as in one dimension. They're easy to understand. So let's assume, for example, that input vector x is of size n, which is the number of pixels, corresponding to n pixels in a one-dimensional image. And the vector kernel k is of size L. Okay, so let's say for now that L is an odd number, just to make things easier. All the ideas carry over to higher dimensional cases. So whatever we do now on one dimensional, it's easy to extend to higher dimension. So this is how we write convolution using the convolution symbol. If you have taken calculus, you already have seen this symbol before. So z equal x convolution k, and this is in calculus is defined as integration with one shifted function. Here we define the convolution result zi as a summation instead for j equal 1 to L, where L is the size of the vector k of kj xj plus I minus L plus 1 over 2. So in other words, for each output position I, we take the dot product between the kernel k and the snippet of x centered on xi with width L. So that's what this equation does essentially. So this process can be illustrated here on the left-hand side of this graph. Okay, so we have a kernel vector of dimension 3, which is plus 1, minus 1, and 1. These are the three elements of our kernel vector. And what it's doing is that it's going to detect darker points in a 1D image. So notice that in this example, the pixels on which the kernels are centered are separated by a distance of 2 pixels. So we say the kernel is applied with a stride s equal 2 because we skip 1 pixel and then we apply the kernel again at the next one. So notice that the output layer has fewer pixels. Okay, so we started here with 3, 5, and 2, 7 pixels, and then the output layer has only 3 pixels. And because of the stride, the number of pixels is reduced from n to approximately n divided by s. So we say roughly because of what happens at the edge of the image. Okay, here and here. The convolution stops at the edge of the image, but one can also pad the input with extra pixels, either zeros or copies of the last pixel here, so that the kernel can be applied exactly n over s times. Now for small kernels, we typically use the stride s equal 1. So this way, no need for padding. We can just keep shifting the kernel by 1 pixel every time. So in this case, on the left, you can see that the kernel size L is 3 because it combines 3 pixels. And the stride is 2 because we skip 1 pixel before applying the kernel again. And the peak response is centered on the darker, lower intensity input pixel. The results would usually be fed through a nonlinear activation function before going to the next hidden layer. So we would take the output here and then feed that into a sigmoid, for example, or redo activation function, and then move on to the next hidden layer. In this case, we have the first 2 layers of a convolution neural network for a 1D image with kernel size 3 also, takes 3 inputs, but here the stride is 1. We added padding to the left and right, so these don't exist here. These 2 pixels are not in the image, but we padded them. We can just copy the last one here and the last one here. And this to make sure that the hidden layer is the same size as the input, so it doesn't get smaller, as you can see here. So shown in red is the receptive field of a unit in the second hidden layer. Generally speaking, the deeper the unit, the larger the receptive field. So this unit right here gets input from three units, which themselves correspond to these 5 units down there in the original input vector. So that's the idea of using kernels to shrink the size of the input vector while maintaining the spatial features of the pixels. Okay, they're not just randomly shrinking. So if we look at the operations then of applying a kernel across an image, it can easily be implemented, okay, using a nested loop, or it could be formulated as a single matrix multiplication. Okay, so just like the application of matrix weights, for example, the convolution we just discussed here with the kernel with L equals 3 can be viewed as this matrix multiplication here. So that's our input vector. This is the kernel shifting with stride equal 2, as you can see. Between the top row, the next row, we shift 2 pixels. And then the result is only 3 units. So that corresponds to what we did on the left right there, using matrix multiplication. So the kernels appear in each row, shifted according to the stride relative to the previous row. As you can see, the matrix is mostly zeros, so it's a sparse matrix. So typically we don't really construct this matrix because it would just be inefficient to calculate with it. Okay, let's continue in the next part.